Now we are going to study about the elements of Earth's magnetic field. The Earth's magnetic field at a place can be completely described by three parameters. These parameters are called elements of Earth's magnetic field. They are magnetic declination, magnetic dip, and the horizontal component of Earth's magnetic field. Here the first one, magnetic declination. It is the angle between geographic north and magnetic north. So this is the geographic north, that is the true north, and this is the magnetic north. So the angle between these two, that is known as the magnetic declination, and is represented by D. And this magnetic declination arises because the magnetic axis of the earth does not coincides with this geographic axis. Okay. And this declination is greater at higher latitudes and smaller near the equator. So as we go up, then the angle between true north and the magnetic north increases. Okay. So it is greater at higher latitudes and smaller near the equator. And the magnetic declination in India is small. That is some 0 degree 41 minutes east at Delhi and 0 degree 58 minutes west at Mumbai. Okay. So this is the magnetic declination in India and it is small. Okay, clear. So that means the magnetic declination at Delhi and Mumbai are noted here. This means that the north pole of a compass needle almost points in the direction of geographic north. Okay, so the declination is small. Then second element, angle of dip or magnetic inclination. It is represented by the letter I. So it is the angle made by Earth's total magnetic field B vector with the horizontal direction in the magnetic meridian is called angle of dip at that place. So this angle of dip is different at different places on the surface of the earth. So you consider a dip needle, that is just a compass needle, and this compass needle pivoted, that is it rests horizontally, so that you made the dip needle to rotate freely in a vertical plane coinciding with the magnetic meridian. Okay, so what happens there? It orients itself so that its north pole finally points exactly in the direction of Earth's total magnetic field. So here this is the magnetic meridian and this is the total magnetic field of the earth. So the compass needle oriented like this. So the direction of the compass needle gives the direction of Earth's total magnetic field. That is the axis of dipole. Okay. So the angle between the horizontal direction. Okay, the angle between the horizontal. This is the Earth's horizontal. Okay, so we are keeping the compass needle on the surface of the earth at point P, and this is the horizontal surface. And the dip needle oriented in this way along the Earth's total magnetic field, that is along the magnetic meridian. So the angle between the horizontal and the final direction of the dip needle gives the angle of dip at that place. Clear? So once again, the angle made by the Earth's total magnetic field. Okay, angle made by the Earth's total magnetic field B vector with the horizontal direction in the magnetic meridian is called angle of dip at that place. So at the equator, okay, when you place this magnetic needle at the equator, the dip needle rests horizontally. So this indicates that the angle of dip is 0 at the magnetic equator. But when you keep the dip needle at the magnetic poles, it rests vertically. So this makes the angle of dip 90 degree. Clear? Then at all other places, the dip needle, that is the angle, okay, the angle of dip lies between 0 degree and 90 degree. Clear? This figure shows the angle of dip and angle of inclination. So here this is the true north, and the angle between the horizontal and the total magnetic field of the earth, that is known as the angle of dip or the magnetic inclination. So, and the angle between true north and magnetic north, that is known as the magnetic declination. Clear? So, if the dip needle rests horizontally, then the angle of dip equal to 0. If the dip needle rests vertically, then the angle of dip is 90 degree. Okay. The third element is horizontal component of Earth's magnetic field. It is the component of Earth's total magnetic field B vector in the horizontal direction in the magnetic meridian. From this figure, you can understand the horizontal and the vertical component of Earth's magnetic field. So here the Earth's magnetic field BE splits up into HE, that is horizontal component, and ZE, that is the vertical component. So we can write HE equal to BE cos I and ZE equal to BE sin I. The horizontal component HE, or we can write BH equal to BE cos I. So this is the horizontal component of Earth's magnetic field. Similarly, the vertical component ZE, that is noted as BV equal to BE sin I. Okay. So, at the magnetic equator, if the angle of dip is 0, then we can write the horizontal component BH equal to BE cos 0 equal to BE. So, at the magnetic equator, the horizontal component of the Earth's magnetic field is equal to the total magnetic field of the Earth. Then, at the magnetic poles, the angle of dip equal to 90 degree. So, the horizontal component of the Earth's magnetic field BH equal to BE cos 90 equal to 0. So, at the magnetic poles, horizontal component of the Earth's field is 0 because angle I equal to 90 degree. That is, the dip needle rests vertically. Clear? So, therefore, the magnetic, that is the horizontal component of Earth's magnetic field is different at different places. So, I think you understand the three magnetic elements of the Earth. What is the relation between elements of Earth's magnetic field? So, we can write BH equal to BE cos I, BV equal to BE sin I. So, from these two equations, we can divide BV by BH, that is equal to BE sin I divided by BE cos I, that is equal to tan I. Therefore, we can find out the angle of dip tan I equal to BV by BH. So, I equal to, we can write tan inverse of BV by BH. Similarly, if you square the first two equations BH and BV, we can find out the Earth's total magnetic field. That is BH square plus BV square equal to BE square cos square I plus BE square sin square I. So, cos square I plus sin square I, that is equal to 1. So, we get BE square, that is the Earth's total magnetic field. Therefore, the Earth's total magnetic field BE equal to root of BH square plus BV square. So, all these equations, that is, this is the equation number 1 and this is the equation number 2 and this is the equation number 3. Okay. All these equations 1, 2 and 3 are the different relations between the elements of Earth's magnetic field. By knowing these three elements, we can determine the magnitude and direction of Earth's magnetic field at any place. Okay.